All right, so today, for those going to lab today, this is the first quiz in lab today, okay? And for the people that have lab on Mondays, then you'll need to wait until your next meeting to take quiz one. That's how that works. So last time we left off looking at these basic topics. We talked about variables. Variable names, by the way, I didn't mention this yet, but variable names are case sensitive. So Alice with an uppercase A is a different identifier than Alice with a lowercase a. That's called case sensitivity. These are the data types, the primitive data types that we're going to use in this class. A char is of size 1 byte. It represents a character or just a value. And an int, which is short for integer, occupies 4 bytes of memory. And a double, and that's short for double precision floating point number. A floating point number is a number with a fractional component. And doubles are of size 8 bytes. And then the fourth primitive data type is bool. And that occupies 4 bytes because the underlying data type underneath it is int. And these are the 4 main primitive data types that we use in this class. But there are other data types, and you can look at those and study those. But these are the ones you need to know for this class. Those are called primitive data types. There's also something called a complex data type, and a string is an example of a complex data type. Here it is. So we declare a string S like this, initialize it to the character sequence HI. That's what that looks like. Here's an empty string, a string that has no characters in it. It's still a string. Strings have a size function, and you invoke it with something called the dot operator. So it's the variable name, period, or dot, followed by the function name. And this forms an expression that evaluates to something, and this evaluates to the size of the string S. The size of a string is the number of characters in the string. So S has 2 characters, H and I. So this statement prints 2 because S.size evaluates to 2. That 2 becomes the right-hand side of an output operation. The left-hand side is the cout, which is called the standard output stream. Standard output stream is the console window. Now T is an empty string, so T.size returns 0, so we print 0 there. Anyway, string is a complex data type. Complex data types have have functions that you can invoke on them using this dot notation. Later on, we'll be defining our own complex data types. They're also called classes, but we'll look at that later on. We looked at variable initialization. And here's an example of an operation on a string. We take what S is, and S is high, the characters H and I, and then we use this operator here. And the right-hand side of that operation is another string, space Bob. And so it concatenates these characters, space Bob, onto the existing characters in S. So the result, when we print it, like here, we print the string S, the output will be hi space Bob. So this is an example of an operator. Now this operator also exists for primitive data types as well. So for an integer variable, this adds a value into an integer variable. Let me give you an example there. We have an integer I which equals 3, and then we do I plus equals 2. And then if we print I, what do we see? What does that print? 5. That prints 5. So this is main. So main is in SAM. I need to CD into SAM to find main. There it is. Now I can run it. There's 5. This expression here is called a literal. This is a character literal. This is a string literal. Sorry, a string literal. A literal, it's what it is. It's just the characters that we see. This is not a literal, this is a variable. This is an integer literal here. It's just what it is. It's not replaced by something else. Here I, so if we printed 7 here, this is a literal 7. But if we put an I there, it's not a literal. It's replaced by what it stands for, which is 5 in this particular moment. So character literals are enclosed with apostrophes, and string literals are enclosed with quotes. And these strings, these are simple strings, simple characters. And we can't have, these are called ASCII characters actually. Or something like ASCII, which is a simple set of characters. It doesn't include things like Chinese characters or Arabic characters and so on. And there are basic characters, like a D and an E and so on. And then there are special characters that are not visible in the normal way, but they have effects on programs that process them. And the new line is one example. The new line character is the value 10. So in the computer memory, in 1 byte of computer memory, you'll see the number 10 here that represents this new line character. So 10 represents a new line character. So in this string, in source code, we use \n to designate 10, the character value 10, which programs normally interpret as a new line. And there's other values that can be escaped. Let's take a look. So if we print T here, you'll see where these ends are, we'll get a line break. What about tabs? \T, that's a tab. So we'll do, after the tab, we'll do a line break, and then we'll do another tab. So that should be tabbed over. Well, the first one is not, so we should have put one in there, right? Let's put a tab in front. Oh, we want to put the break first, and then the tab. There we go. And there's other characters. There's we can do R. R is called a carriage return. Actually, these come from the old days when we didn't have electronic we didn't have these display screens. At a certain point in time, they used like typewriters called teletypewriters. And to interact with the computer, you would use a paper. So they would have to, type things on the terminal like a typewriter and would type on the paper. But that would be transmitted into the computer, and then there would be output as well on paper. So it would not be on a like a television screen. What do they call it? The CRT, they used to call them, cathode ray tube. So you had this print head, and these characters controlled a print head. So a carriage return means there's a carriage, there's a cylinder on the typewriter that would have to turn. And so that the R here, that's character 13, by the way, carriage return, would turn the cylinder, one line. And then the new line would make the type head slide all the way to the left to start the new line. So if you just did, carriage return, you'd just stay in the same column position. You wouldn't readjust to the beginning of the line. It just moves the cylinder. But this will have the same effect now. So you can think of the console as being typed, using like an old typewriter. But see, this carriage return has no use anymore. But it got embedded into things, so it's stuck there, and we have to deal with it. And I'll give you two examples. On Windows will terminate its lines internally with carriage return line feed. So this sequence is used in Windows text files. But on Unix systems like Mac OS X and Linux and other Unix systems, they don't use the carriage return. They only use the new line characters. So you'll see inside their text files, you'll only see new line characters, character 10, value 10, as for terminating a line. But that's not where it stops. On the internet, you have machines, computers talking to each other to convey information, like to send email, to send router tables, to send data from one computer to another. So you have these different protocols. And most of the protocols, well, at a certain level, at the application level, so at the deeper levels, the protocols are not character-based. But HTTP, for instance, take the HTTP protocol. You see up here, HTTPS, as part of the URL, that designates a protocol. And this protocol has defines messages are sent between the client and the server. And the messages have data, and the data occupies what's called the body of the message. But just before the body of the message is sent, you have a header section, and the headers are like metadata, talking about the type of data in the message, timestamp, information about the message being sent, what the recipient of the message might need to know about what kind of character encoding is being used. Maybe there's compression that's being used to make the message data smaller, and so on. So these headers are transmitted, and they're character-based, so they just look like you can read them. And there's a bunch. The headers are in the form of lines, and each line is terminated by character return line feed. So the HTTP header lines are terminated with this sequence /r/n. So you see it. You see this old, unnecessary character sequence that's being used in internet protocols. I think email might have a similar situation as well. So sometimes you have to deal with these carriage returns, and sometimes you don't. So it's interesting when it comes up, but certainly has no real use. This is just like some people say the appendix has no use in the body, right? It's just there. You can take it out without any effect. I don't know if that's true, but that's what I hear. Right? That's common knowledge. So this R is like that, or has no real use. But we have to deal with it. So that's a long-winded explanation of something maybe simple. What about the assignment operator? So we've got different kinds of operators. This is the strings. We've talked about that. This is the assignment operator. Once you define a variable, say k in this case, and then you can assign values to it. You assign 3 to it, so on. So we have an integer k. We can assign a 3 to it. And then when we print k, it'll print 3. After we assign to k and use k, we can change its value. We can set it to 6. And if we print k again, it's going to print 6. So variables are they have their state can change. They represent, a portion of memory that contains data in it, and that memory is changeable. So we say it has a state. The memory has a state, and this changes the state of memory. It looks something like it's a memory. When you look at it as representing numbers, memory is a sequence of zeros and ones. So a byte has got 8 Boolean values. A 0 or a 1. If we restrict ourselves to zeros and ones, that's a data type called bool or Boolean. So a byte is 8 of Boolean values, one after another. So the 6 would, look like something like a 6. Looks like 110, but in base 2, that's 6. This is the ones. There's 0 ones. These are the 2s. There's 1 2, and these are the 4s. There's 1 4. So 4 plus 2 is 6. So this is the number 6 in the base 2 number system. In the base 10 number system, it's our normal 110. In base 16, it's, well, it would be 1 times 16 squared plus 1 times 16 plus 0. So this is 16 squared, right? So what's 16 squared? Like 256, I think. And 1 times 16 is 16 to the 1. So that's just 16. I'm converting this to decimal. So 110 in hexadecimal in base 16, and we designate it like this. It goes 0x. So in C++, if we were to see this representation here, we'd say, oh, that's base 16. And I'm converting that into base 10. What is that? 272, base 10. And then there's, you could also represent base 8. So base 8 would look like this. If I did 0, 1, 1, 0, that's because I have a leading 0 there. The compiler is going to think, oh, you mean base 8. So that'll be, if I convert that to base, here I'm converting that to base 10. If I convert that to base 10, you know, it's 1 times 8 squared plus 1 times 8 to the 1 plus 1 times 8 to the 0, which is just 1 times 16, sorry, 1 times 64 plus 8 plus 0, which is 72. Wow, that looks like the 72 right there. And you know, this by itself sorry. 110 by itself, the compiler looks at this and says, oh, that's just, that's base 10. This is base 8. This is base 16. Let's see if we got it right. We'll do this experiment here. Watch this. So first we'll print 0x110. And then we're going to print 0110. And then we're going to print 110. Let's see if I got it right. I'm a little nervous I got it wrong, by the way. I never did this before in class. Oh, got it right. Now I have more faith in myself. And I mention that because this is what you got to do. You know, I mean, you got to do these little experiments. I'm doing them up here for you. Right? I don't really need to do it. I'm showing you what I think you should do, which is to play around, test your knowledge, build your confidence that what you think is true is really true, and carrying out experiments. So this could be a source of some bugs. I didn't know this, by the way, until a couple of months ago. That's interpreted as octal. They call it octal. If you have a leading 0 in an integer literal, the compiler treats it as base 8. So I didn't know that a year ago. Maybe I did. Maybe 15 years ago or something. I came across that information, but I never had to use it in all that time, and I just sort of forgot about it. And I was reading, and I said, oh, really? So there's the experiment to prove it to myself. But that's just this language. That's only C++. Other languages probably don't assume octal. Other languages might use this notation for base 16. Hexadecimal, they call it hexadecimal notation. But octal is not common at all. Hexadecimal is common because a byte is 8 bits. And that can be represented by very nicely with hexadecimal numbers. Right, so each byte, like if I look at this, FF, if I do 0FF, let's do some experiments, this might be interesting. If I do, 1 is 1, right? And if it's base 16, it's still a 1 in base 10. Oops. Well, what's that? Anybody know this number? In base 10. This expression in hexadecimal notation represents what number in base 10 decimal notation? Anybody know? I'm the only one that knows what's going on right now? Okay. I guess that means you belong here. All right, so, remember how in decimal, these are the ones. That's the ones. These are the tens, right? These are the hundreds. There's 2 100s. It's 110 and 0 ones. Well, these are the ones, and these are the 16s because it's base 16, right? And then the one in front of it, that's the 16 squares, the 256s. So this should print, well, that'll print 10 as a decimal, and then this prints 16. Because actually the output stream, the number is just a number. Whether we designate it as base 16 or base 10, it's just a number. And you can think of it as, 16. I don't know where I'm going with that, but let's see what that looks like. Here it is. So what was I going to say? Something about bytes. Oh, yeah. So this is the maximum to fit in a byte. So that's 255. Because it's F is 15. So it's 15 times 16. I'll do it up here. So F is 15, and we want 15 16s, plus we want another 15, right? So that's 15. That's 15 16s. So this expression is the same as this expression. $255. So a byte can hold. A byte has 8 bits. So it's got, it looks like this. Sometimes you see it like that. We've got 8 ones and zeros. And this number here, FF, is where we set every bit to 1. I put a little space in there because it's easier to see it, right? 8 strung together is too hard to read. So that is the binary representation of hexadecimal FF, which happens to be the decimal notation of 255. I mean, in decimal notation, it is 255. So these are nicely grouped together. If you see this in binary, see this is 1, 1, 1, 2, 1, 4, and 1, 8. Because see, in decimal, I'm sorry, in binary, it's powers of 2. So it's 2 to the 3 plus, let me group it up like this. This first one, you know, it's 1, 2 to the 3s, plus 1 times 2 to the 2, plus 1 times 2 to the 1, plus 1 times 2 to the 0. Anything to the 0 is 1. So if we look at this, 2 to the 3, let's see, that's 2 times 2 times 2, that's 8. You know, plus 1 times 2 to the 2, that's 4. 1 times 2 is 2. And 1 times 2 to the 0 is 1. 2 to the 0 is 1. So that 4 plus 2 plus 1 is a 15. So this half byte is 15. And it can look at the, so when we have a byte is 8 bits. So you can look at a byte as having 2 chunks. There's a high chunk and a low chunk. And so we can easily represent that in base 16 like that. That's the reason they use base 16, because base 16 is an easy way to represent binary data, or data that's represented using binary system. A computer memory is a string of 1s and 0s. But we don't think of it usually as 1s and 0s. We think of it as bytes. Because a byte is in the CPU is the smallest unit of memory that can be addressed directly, so a byte. So everything's, in memory, bytes are numbered. You have byte 0, byte 1, byte 2, byte 3. All right, so you've got 8 gigabytes of RAM. They're all numbered, starting at 0, going up to 8 gigabytes minus 1. And each byte looks like this. So each byte, instead of looking at it like this, when maybe you want to display the value of a byte of memory, instead of looking at it as in its binary form, we look at it in its hexadecimal form, because it's easier to stare at. FF is easier to look at. And of course I put a space in there to make that easier to look at. But see, this is just, people think this is easier to deal with. That's how they do it. And sometimes they'll just, you know, put it in decimal, you know, so these all mean the same, it's all the same number. These are all the same number, but they just have different representations, you know, using different systems. And we won't be working with this that much, or very little. We'll work with this just a little bit. But when you take courses after this course, then you have to deal more with hexadecimal values, binary data directly. Okay? So you need to have some understanding of this. All right, what about this business here? Arithmetic operators. So we have, let's try to understand, these things. Like, what does that do? What's the difference between plus plus k and k plus plus? Let's take a look at that. Joseph k is 3. I think we talked about this last time. What does that print? It's getting pretty boring, right? Like getting people? And that prints 4, right? Okay. What does that print? First it prints 4, and then what does it print?
It's 3.
Prints 3. That's right. I think I see that. 4 and 3. Okay. What about this? What does that first line print right there? And that means increment k. So I'm going to increment k. So it's going to print 4. Okay? What does that line print? 4. Because we're modifying k. Before, we weren't incrementing k. We didn't modify k. We used k in an expression that evaluated to 4. Now, we're modifying k so k becomes 4. And this thing also serves as an expression that evaluates as 4 as well. It's like a side effect. It's an expression that evaluates to 4, but it also has the side effect of changing k so that k is one larger. So this will print 4, 4. I'm building up to the big challenge here. You ready? Okay, so we got to get the money on the table for this one, okay? We're going to have that betting. What's that going to print?
3 and then 4.
Going to print what?
3 and then 4.
3 and a 4? 3 and a 4. Everyone agree with that? Ready to bet? Put our money on the table up here. Just kidding. Trying to get you invested in this so you can concentrate a little more. Yeah, 3 and 4. That's what it prints. So you must have been reading it ahead of time here. You took away the magician's trick. I got to look for another trick to impress you with. All right, 3 and 4. You see, because this expression evaluates to what k is before it's incremented. This expression evaluates to 3, and then k is incremented. That's different than this one. Here, the expression, we increment k first, and change k, and now the expression evaluates to what k is after the increment. Yeah.
What would happen if you did that, but you put the k in parentheses?
If I put k in parentheses?
Yeah. Does it then?
No, that won't work. It won't compile. I'm saying it won't compile, and I never did this before, but I don't think it'll compile because you can't increment an expression. This is the result of an expression, so you can't increment an expression. This, by putting parentheses around the k, you've formed an expression. You cannot increment an expression. Like we can't do this. We can't increment, the result of 2 plus 7. So by putting k inside parentheses, this becomes an expression just like 2 plus 7, and we cannot increment that because the increment wants to modify memory. And the result of that expression, by the way, is in some form of memory. It's in what's called a CPU register. And we could increment the register, of course, but the language does not let us do that. And I say that without having ever tried it before, but just sort of thinking that, oh, it worked. Wait a minute. This is letting me do that? You know what? I think it's something funny there.
I can try that on
Cloud?
Plus if you want.
Yeah, try it on yours.
I know Cloud 9 lets a lot of things pass through.
How about that? Is that going to work? Well, I'm wrong up here sometimes. It's too bad we weren't betting on that one. You guys could have just, I could have walked away poor today. All right. There it go. Finally. It's failing. Had to work at that. This is what I thought it would do. Probably what happened was the compiler did some kind of optimization and it just said, oh, you don't need the parentheses. Maybe it's some kind of optimization that was performed. How do you turn off optimization? Let me see if I got that right. How to turn off C++ optimization. Clang is the name of the compiler I'm using. There's so many options. How do we turn off optimization? See, it's, how can I do that? I gotta have to faster link.
I just tried it on a terminal.
Huh?
I just tried it on like a Linux terminal on board.
It's okay there? Oh, this optimization level. Oh, minus O0. So this works. Still works. Anyway, I got it wrong. I'm down one here. So, but once again, what about that one? That'll fail. That was a good experiment. Nice one. Okay, so did minus minus is the same as plus plus, just decrementing instead of incrementing, okay, decreasing by one. So you can get to these. Let's look at this activity here. Look at the example quiz questions, all right? Here's the quiz question. What does this print? Let's do a quiz question now, just to warm up. I want you need to practice these quiz questions. What does this program print? This is a quiz question. You know, I have never run this. I just look at it and I figure it out in my head, and that's how I grade the quizzes. But I've never run it. But let's do that. Let's figure it out in our heads. You know, put some money on the table, and then run it. See who wins the money, loses money. Yeah.
I want to say 0.
Prints what?
0.
You think it prints 0?
Alright, hold on. You need to do the plus K. I think it's 3.
Print 0. Any alternatives?
3.
3? Maybe 3? Got 2 guesses. I said we got a bet going on here, right? We got some ego invested into this here. All right, so this is going to be on the quiz, not this exact problem, but something like this. You'll have to solve something like this. Yeah.
Can I actually change it?
Yeah.
I think
Good.
it's gonna be 7.
You're going to go with 3? You're gonna
7.
7? I saw some heads nod back there with 7. I don't know what it is yet. How many people think it's going to be 7? I didn't look at it yet. Let's get halfway up is all right. You can, if you're not sure, don't go like this. Just do that, okay? Does everybody have a guess? You should have a guess. You've got to have a guess. Unless you're like, I mean, it's summer, right? We all feel super lazy and we don't want to have to think. But this is, you have to develop this new muscle here to exercise that muscle. You gotta think it through there. How about, let me do it like this.
I think it's gonna bring 4.
4? We got a revision there, 4. All right, I'm gonna think out loud here. Yeah? What?
Now I'm going
10? 10. But we have so many possibilities. Yeah, it's like a horse race now. We only get one winner, or it may all be losers. Keep working on it, but what I'm going to do, I'm going to show you a little trick that you might want to try doing. I'm going to do this. There's an N here, okay? There's an N in it. At this point, remember, this stuff here, these statements execute sequentially. This statement completes, all right? And then after that completes, the next statement in line 7, that completes. After that line completes, the next statement completes. So there's 3 statements in this program. Now each statement is got built up using expressions. So look at this last statement. That's an operator. That's an operator. That's an operator. That's an operator. There's 4 operators there. But you can't do all 4 operators at the same time. One operator has to be done when the others are waiting. So they're done one after another. So you got to figure it out which operator goes first and which operator goes second. And when the operator goes, what effect does it have? And then the expressions are then these operations, evaluate the things. The expressions evaluate. As if I do 2 plus 3 times 4. And you see in math, you're going to say that's 14, right? You're not going to say that's 24 or 20. You're going to say that's 14 because 3 times 4 is going to go first. Oh, to make it different, I'd have to use parentheses, right, to change the order of execution of those operations. But if I left that out, I got to say, well, this has higher precedence. Multiplication has higher precedence. It goes before any addition happens. So this has lower precedence. That's the normal rule that we're taught, learning how to do math in school. And the compiler follows those rules as closely as it can. But, we've got other operators that this is not part of math, right? This is another, but it's nevertheless, it's an operator in this language. And this has the lowest precedence. So this is the thing that goes last. And you know that this plus goes after that multiplication. And plus plus n, well, because it's a pre-increment, it's called pre-increment as opposed to the post-increment here. The pre-increment goes first. So that's the thing that goes first. And then this thing I've highlighted is an expression. It gets replaced by some value. It evaluates to that value. That's used then in the next level expression. And that plus plus n evaluates to some value. Then it's used as the left-hand side of this multiplication operation. And this result, this expression I have highlighted right now, becomes some value, which becomes the left-hand side of this addition operation, and k being the right-hand side. And then this whole expression is now evaluated to something. So we have a number for this. That becomes the right-hand side of this output operation. So that's the number that we send out. So that's how we have to go step by step and see, how it computes. So now it's hard to keep everything in your head, so you might want to keep track of the state of the variables as they change, as you evaluate each operation one after another, and evaluate expressions one after another. So this first statement is easy to evaluate. We just create an n, initialize it to -1. The next statement is more complicated. We create a k. So I've done that over here using my notes. So I could forget about n for now, because I wrote it down, what n currently is. And then remember, n represents memory, so n is going to change. N is going to change. It's not -1 forever. And when we get down to here, n is not -1. It's something else. K is something else. These variables are things that change. Now, so to assign, this is the assignment. Assignment here is get the lowest priority. That's done last. So we have to evaluate this expression. And this is a tricky one. When we evaluate this expression, we'll write it into k, store it into k. How do we evaluate this expression?
It'd be -1 times -3.
Huh?
It'd be -1 times -3. Does your increment
Yeah, -1 times -3, because see this expression here, this evaluates to n. It evaluates to -1, and after it does that, it increments n. So this expression evaluates to -1 because it's a post increment. So this that I have highlighted is -1. I'm going to pull out -1, but then n gets incremented. So n becomes 0. N becomes 0. I'll do it like this to show the changing state. N becomes 0. But this expression, nevertheless, was evaluated. Before we set n to 0, this expression was evaluated to -1. So we have this expression now, -1 times -3. So that's 3. So this thing I have highlighted right here, this expression evaluates to 3. We assign 3 into k. So we're not relying on our memory. We're just we're relying on our memory as little as possible. So we're making notes here on the side. K is 3 and n is 0. I just showed you this. I left that in there so you could see what the progression of values it takes on. So line 7 is finished. What about the next line? We need to evaluate this expression. Well, this has got the highest precedence, this plus here. So we evaluate this expression, plus n.
So it becomes a 1 now.
We got to increment the n first. And then the expression evaluates to the result. So we're going to increment n to 1. Now we incremented n to 1. Now, this expression evaluates to the new n, which is 1. So this becomes 1. It's different than the n plus plus. So 1 times 4 is 4. So that expression evaluates to 4. And then we've got 4 plus k. What's k? 3. So 4 plus k is 7. So this expression evaluates to 7. A 7 is the right-hand side now of the output operation. This expression also evaluates to something. And I'll ask that in a second. It has a side effect. This expression evaluates to C out itself. That's why we can, do this. That expression itself evaluates the C out. That's why we can cascade this. That's why what it evaluates to becomes the left-hand side of the next output operation. Yeah.
In C out, it uses K, so since it's using K, does it increment it after it's used K again?
Increment what?
N? Because K equals is N
No,
times
no.
3.
No, because it's a pre-increment, so it'll increment n before it's used.
Yeah, but like, let's say after it sees it out, it says it's 7.
Yeah.
N
I mean, after this output operation runs?
After it outputs it,
Yeah.
does it now become 2 because K increments N?
No. That's the past. We're not going to repeat the past. The past happened already. So things are done in the sequential order.
I think he's asking because K is defined as having an N.
Oh, because of up here.
Yeah.
N.
Oh, no. We
Because
do
you
not.
use K.
This is a specification of an activity. We don't go back and repeat that activity.
Even if you use K like later on.
Yeah.
It only
Yeah.
evaluates to that.
Yeah, this is completely disconnected from what happened in the past. This is the past. This doesn't represent a condition that holds forever. This represents doing something. You do it once and then that's it, and forget about it. It's a sequence of operations. Does that make sense?
Mm.
Okay. The question is perfect because this is, I teach this class a lot, and students, they all get fuzzy on this. They don't quite get it because they're used to thinking more in math terms. Like in math, you'll see a set of equations, and that represents, like, these equations represent a relation that just exists. It's timeless. It's just what it is. But when you're looking at source code, it doesn't represent timeless relations. It represents a sequence of activities or operations. When you do it, it has an effect, and then that's done. And then it's just, in a sense, discarded, and we move on. Unless, I'm simplifying a bit because sometimes you'll see later on we'll do things and operate on some kind of a thing and change the state of something, and later on, that has an effect. But anyway, I don't want to get into that. So look at that. That was the first guess. I'm going to call it a guess, right? That was the first guess. So that old, what do you call it? Wisdom that you hear, go with it. The first hunch is right, don't change your, but I don't believe that actually. I think that the first hunch is sometimes wrong. But anyway, we didn't run it yet, so we don't even know. So I've been wrong today once already, right? So I've been humbled. So I'm gonna vote with 7. Is anyone else gonna?
It's not gonna run.
Huh?
It's not gonna run because you have N and K on the side. It's not gonna run because you have N and K right now and you didn't put it in comments.
It's not gonna run. Oh, because of this.
Yeah.
Right. It won't compile, right? That's right. It won't compile. So anybody think it's So my analysis is 7, or our analysis together. Is there anyone else is there anybody who thinks it's not 7? Any big time gamblers here, you know? Okay, because you could win big here if you bet against us and we're wrong. All right. Let's see. 7. Okay, I got it. So that's an example of a quiz question. So you got to know how to do that. What do you got? 1 or 3? We're spending a lot of time. Here's another one. Let's look at that quiz question. This is not today's quiz. This is the subsequent quiz. Today's quiz 1 is on command line interface. What about this one? What does this print? What does that print? So everyone should, well, let me tell you what the issue is, okay? That's division. That's division. But there are 2 different kinds of division. This first division is integer division, and the second division is floating point division. Unfortunately, it's the same symbol, slash, but they're 2 different operations. They're similar, but they're different. Because floating point division results in a floating point number. And integer division results in an integer number. And an integer doesn't have a fractional component. Now, why is this integer division? Because the compiler looks at the 2 operands, 1 and 3, the numerator and the denominator. This is an operation. It has a left-hand side, which is 1, and a right-hand side, which is 3. The compiler says, well, your left-hand side, your right-hand side are both integers. And so I will perform integer division. I'm going to produce an integer result. And then the compiler gets to the next one, and it says, oh, your left-hand side is an integer, okay, but your right-hand side has got a decimal point in it. That means it's a floating point number. So I'm going to perform floating point division. The result will have a fractional component. So what does it print with that information I just gave you?
0.3.
Huh?
0.3.
0.3. Or 0.3333, like that, right? Because, look, let me tell you, let's do it like this. Let's suppose you are the compiler writer. You know, compilers are programs. They're written by people. Suppose that you're going to write the compiler. And you're writing it, you're going to interpret this symbol as integer division. What would you make 1 divided by 3 compute to as an integer result? What would you make it equal? Huh? Well, you have to. That's the requirement. The boss says we've got to have an integer division here. You know, you've got to make it up. What would you make 1 divided by 3 equal if the result has to be an integer?
0.
0. Yeah, you'd make it 0. What about that? What would you make 2 divided by 3?
1. 0. 0.
Huh?
0.
Okay, you can make it. What's the other option? What if I told you, what would you make this? If I told you, 99 over 100. I said, okay, just do 99 divided by 100 and give me the result as an integer. I don't want fractional stuff. No, that's messy. I just want you to give me the integer result. What would you, as a human, what would you think of to produce here?
One.
1, right? I mean, it's 0.99. Aren't you going to round it up to 1? But as a compiler writer, you have to decide whether you want to round it or not round it, right? So what do compiler writers do? Do they round up, round down? You know, round up if it's 0.5 or larger. Round down if it's less than 0.5, the fractional component. What would you do as a compiler writer? Well, anyway, that doesn't matter. You're not a compiler writer. What did they do? What do they do? And they all do exactly the same thing. Nobody changes. Nobody does anything different. They all do not round. They truncate. So if the result is 0.99999, they're going to produce 0 because they don't round up. It doesn't round up. It truncates. It discards the fractional component. So 1 divided by 3 is going to be 0, plus 1 divided by 3 here is going to be 0.3 repeating. And so it's 0 plus 0.3, so it's just 0.3. There's the 0.3. I didn't hit the new line, but so it got merged in with the prompt. Okay. We're running out of time. Almost done. What do you think about that? I got to tell you, this is the source of a lot of errors. And this is an issue that's pretty much in most languages. Yeah.
If you put an at next to the 3 and make it a floating point number, would it add them together?
Wait, start again.
If you put an at next to the 3 and make it a floating point number, which is the same thing as 3.0, what would compile similar?
So put a what?
An F.
An F?
Yeah.
Yeah, you can do that. Let's do that. Okay, this is without it. All right, 0. Let's put an F. We say we want it to be a floating point number. Is that right? Does that compile? If that compiles, no, it doesn't work. Invalid suffix. How do we put it in the front? No. How do you designate 3?
I always thought you just put it right after the number, or maybe you still have to put a decimal point. Maybe you still have to do it. So it might not even make a difference.
Yeah, I think you're right. You're right. That was it. So we didn't have to do it anyway. This means use 4 bytes. Make that number 4 bytes.
So it's short.
And what's double precision? Do you know what that is?
Isn't it just the D?
F? Is this double precision?
That one?
That just means floating point?
Yeah.
But it doesn't make any sense because this should work, right?
Yeah, that's what I always thought would work. I never tried it, so I brought it up right now.
Well, it's invalid on an integer constant. It may work in some languages. Maybe older versions of C++, this works. Yeah, maybe.
So is that if in that specific case you want to treat that integer like a floating point
Yeah, yeah,
number, but it
exactly.
wouldn't actually change after that, it would still be an integer.
I mean, this
'Cause
3F?
I'm looking at 3.0F and I'm like, why wouldn't you just always use 3.0? But maybe-
Yeah, you don't need the F. But the F might specify the number of the precision, how many bytes. You can read about it here. Where is it?
I think it was
This is the reading business here. It's under literals. Now I'm presenting a simplified version of this information here. And so if you want to get more into the details, this is what I talked about earlier. You hear these suffix here. And we can use, you can modify unsigned and long. See, these are examples. It's an unsigned, treat 75 is an unsigned value. Oh yeah, F here. So L is long double and F is float. So this here it's saying treat this constant as being a lower precision 4-byte value. And treat this one as being a higher precision 8-byte value. And actually the number of bytes used is really dependent on the hardware. I'm giving you the values that are typically the result of this. So this L would typically result in an 8-byte representation of that floating point value. This would result in a 4-byte representation. So L and F, but you have to have the decimal point in there, obviously. So this can have, value in certain situations where you're concerned about round off. Because you can get round off here. This could affect your calculations because the number is not precise enough. All right, so that's the reading. It's good to dig into the reading if you want to learn more about this. I'm giving you the kind of like the minimum view of it just to get started. Assignment operators. And I wanted to talk about this. Next time we're going to talk about, make sure I get to this, the modulo operation. This will come up, well, I probably don't need to remember. We'll be doing these problems using the modulo operator. That's down here, that's a remainder operator. I think that's it. We don't want to go over. So that's it for today.